So 11 months ago, I created a riddle about ball half filled with water, and the problem was to find the ratio of the area of the water to the area of the ball. And I was called out on the video because the ball and the water are not 2D objects as I presented them, but 3D objects. And obviously a person who called me out on this is correct. So now I wanted to fix the riddle and wanted to solve it properly. But also I want to take this opportunity to explain the idea of integral calculus and then expressing the idea in maths and coming at what the actual integral is. So let's visualize the riddle a little better. We have a ball that's half a sphere and then it's half filled with water. The height of the ball we can call as uppercase R, and the height of the water will be R/2. We're looking to find the volume of water, and now viewer, it's a perfect moment to stop that video, try to solve the problem by yourself, and then come back when you're ready. This gives you the most satisfaction and it teaches you the most. So back when calculus wasn't around, these kind of riddles were really difficult to solve, because we do have formulas for rectangles, for parallelograms, for rhombuses, for pyramids and cylinders, but we do not have a formula for a part of a sphere. So we have to kind of come up with the formula using the other shapes. So let's say we take cylinders and we fill the water, the space where the water is, with smaller and smaller cylinders. As we fill the space, we can see that if each cylinder is just smaller in height and there are more and more of the cylinders, then we will be able to better and better approximate the volume of the water. So technically, if we had infinitely many of the cylinders, then we would be able to perfectly approximate the volume of the water. And that is the idea of calculus. So the idea seems pretty simple. There are infinitely many cylinders and the cylinders are infinitely small. But now we have to kind of show it mathematically, and that is the most problematic. We can observe that cylinders which approach the top of the ball have higher volume. So we want to be able to find a formula how this volume changes according to some number or some length. So let's say, for example, we want to know what will be the volume of each cylinder given how far it is from the bottom of the ball. We can mark the distance as L. We can mark now R of L, that will be the radius of cylinders based by the distance from the bottom of the ball. Now in order to find how it's dependent on L, we have to create this right triangle as shown and use Pythagorean theorem to find R of L in terms of L. So now we have two very useful equations, but let's say we don't want to know the volume of the cylinders based on its distance from the bottom of the ball, but its index. So which one is it? So we can write the dependence of L on the number of a cylinder, where I is a number of a cylinder. For example, we can see that for the fifth cylinder, L is equal 5 dx. Now we have all of the equations in place. We just have to remind ourselves that we're looking for infinite amount of cylinders, and each cylinder has to be infinitely thin. And we will arrive at our volume of water. So now we can get to work with our equations. First of all, we can substitute the L of I into the R squared of L, and then we can substitute that into the V of I. And that way we're going to get volume of a cylinder depending on the index. So basically, which one is it? Now we can simplify the expression a little bit, factoring out dx. Now we're going to be looking at a sum that's ranging from I equals 1 to j, and j approaches infinity, of all of those volumes. So we'll be summing every single cylinder from the first cylinder to the infinite cylinder. Let's substitute Vi. We can factor out common expressions. Now the sums consists of subtracting two different sequences, so we can break it down into two and factor out multipliers. Now we're left with these two sums of different sequences, and fortunately we do have formulas for them, so let's just write them down. Derivation of these formulas isn't very challenging, so I will not be showing it in the video. We can substitute in our expressions and further simplify the expression. So bring to a common denominator, factor out the division by 6. Now we can remind ourselves that from the bottom of the ball to the half of the ball, we have j cylinders, and each cylinder has a height dx. So we can say that r over 2 is equal dx times j. From that we find dx that equals to r over 2j. We can now substitute dx into the equation and factor out r cubed. We're left with this expression that looks way better. It's just an ordinary limit. We can now split the limits and calculate each one individually. Now let's expand the brackets. In the first limit, we can divide every single expression with j by j squared, and in the second limit by j cubed. We get following expressions. We can see that whenever a number is divided by j or j squared, it will approach 0 as j approaches infinity. Thus we get the solutions 3 over 2 and a quarter. Let's substitute into our expression and further simplify. And we get the volume of our water, which is 5 over 24 times pi times r cubed. So yes, we found the volume of water, and we didn't do it with the use of calculus technically, but we did. So let me explain. Definite integral, more specifically Riemann integral, is characterized as a sum ranging from 1 to j, when j approaches infinity, of values of function f for changing arguments times a variance of x characterized as delta x. This might sound complicated, but only until the point that we realize we use the same sum in order to calculate the volume of the water. Our Vi was the f function and dx was the delta x. So now we know that summing and integrating are very similar ideas, but how do they differ? So let's look at our three equations. Previously, we were using number of a cylinder counting from the bottom of the ball in order to determine its volume. But we don't really care about numbering the cylinders. We only want to know their total volume. That is when using integrals really comes in handy. This integral sums volume of all infinite cylinders exactly as we did, but it doesn't do numbering. But instead we have the lower bound, which is the bottom of the ball, and the upper bound, which is r over 2, and that is the half of the ball. It behaves similarly to a sum, so we can factor out multipliers like pi, and then substitute in the r squared of L. We can split the integral and then again factor out multipliers. Now let's calculate the value of these two integrals. We will use the power rule of integration in the bottom right corner. We calculate definite integral as if we were calculating indefinite integral. When we got the answer, it's like a function. We substitute in the higher bound, and from the higher bound, we subtract the lower bound. That's how we arrive at an answer. Let's now substitute and further simplify. As you can see, we get exactly the same result as we did by summing. Out of curiosity to have the riddle solved, we can calculate the ratio of the volume of water over the volume of ball. And it simplifies to 5/16. Which kind of makes sense because the water is definitely less than the half of the ball. I hope this video kind of helped to get around calculus and what it is and what it's about. So if so, then you can like leave thumbs up and I don't know, a comment or something. Thanks.